Hi, everybody. This is Dr. Nigro with the Chem Calculations screencast. This screencast is going to focus on our second look at thermodynamics. We've already talked about thermodynamics, which is the energetics of reactions in terms of enthalpy. All right, which remember, we represent it with a large capital H, and it is a measure of the heat energy within a set of reactants and a set of products. And in particular, we talked about the change in enthalpy and how that relates to whether a reaction is exothermic, releasing energy, or endothermic, absorbing energy from its surroundings. All right. The rest of this look at thermodynamics is going to focus on entropy and then Gibbs free energy. And we're going to define both of those as part of this screencast. But we really do need enthalpy and entropy to get at Gibbs free energy. So enthalpy is going to be an important part of what we're talking about, but we're going to focus more on the definition today for entropy. If you need to go back to the screencasts on enthalpy, please do so because they are important here. All right, so let's start with entropy. All right, it's a measure of the amount of disorder within a system. All right, now, what do we mean by that? Well, okay, so let's talk about a gas versus a liquid. All right, if I asked you to tell me which one of those had more disorder, hopefully you would say the gas. There's a lot more space, there's a lot more motion, so there's just more disorder within that system. So I would say that a gas has high entropy, whereas a liquid has lower entropy. Now, if we pulled a solid in here, I would say a solid has the least amount of entropy compared to the liquid, and then again compared to the gas. All right. You could also think about it in terms of volume of a gas. All right. So let's say we have a 10-liter container versus a 10 milliliter container of the same amount of a gas, 1 mole of a gas. All right. If you have more space for that gas to occupy, you are going to have more disorder for that gas. You can't predict where those particles are going to be. They're going to be zipping all over the place and it's just going to be a mess. Whereas if you only have a small amount of space, like 10 milliliters, all right, those gas particles become much more compacted and the disorder is going to go away. So that larger volume would be high entropy, and that smaller volume would be low entropy. All right. Yeah, so when you talk about the entropy of a system, these are some things you need to think about. If you're talking about the reactants for a particular reaction and you're comparing reactions, reactions with multiple reactants compared to, say, a single reactant, if you have multiple reactants, you're going to have more disorder because you're going to have a lot more mixing of these components versus a single substance. All right. So when you're asked to think about the entropy of a system, these are the things you need to think about: gases, solids, liquids. What do you have? All right. Do you have mixtures of reactants versus single reactants? Do you have things in larger spaces versus smaller spaces? And that's going to let you start to think about what that entropy looks like. Now, entropy is represented by a capital S. So that is what you see in our formulas for entropy. And similar to enthalpy, we actually like to talk about the change in entropy when you move from one state to another, whether that be a reaction or some sort of physical change. All right. And to calculate that for a reaction, you're going to need to use the same idea that we did for enthalpy. You'll need your balanced reaction with those coefficients, and you're going to multiply the entropy of those products by their coefficients and add them up. And then from that, subtract out the entropy, whoops, of your reactants. All right. So it's going to be a before and after look. All right. Now, the universe loves disorder. All right. So we want our delta S values to be positive. All right. So the universe tends towards disorder. All right. My chemistry professor used to talk about disorder and the universe in terms of leaves in the fall. And he would always say that when the wind blows, when the universe blows those leaves around, they don't blow them into nice, perfect little stacks of leaves. They make a big mess. And that is what the universe prefers, some sort of mess around. All right. So whenever we look at a change in entropy, we are looking for that entropy to be increasing as we go from the before to the after. That is what the universe likes. All right, so we know that enthalpy, we'd like to see energy released into the universe. For entropy, we like to see the disorder increase as we move from the reactant side to the product side. Now, what does that mean in terms of the total energy of the system? Well, that's where Gibbs free energy comes in. All right, now Gibbs free energy is represented in our formulas with a capital G, and this weighs the relative contributions of enthalpy and entropy to determine if a process, whoops, or reaction is favorable. All right, and favorable means will happen, probably. We're going to see there are some exceptions. You can have a positive Gibbs free, I mean, sorry, you can have a favorable Gibbs free energy and the reaction still doesn't happen because the kinetics control that, but that's a different story. We'll deal with that later. All right. So really what we're looking at is the excess energy, the free energy, hence the name Gibbs free energy, left over after the reaction has used what it needs. And this could also be a process, like a change of state or something, but I'm going to focus on reactions. Has used what it needs to run. All right. The universe loves excess energy. It's going to convert that excess energy and do something else with it because we know it doesn't get destroyed, but it's going to use it for something else. All right. So, really, what we want is we want the free energy to be released out into the universe. All right. And we know that from our enthalpy calculations, when energy gets released, enthalpy has a negative sign. Same idea here. When there is extra energy being released out into the universe, Gibbs free energy is going to have a negative sign. All right, so we want G to be negative. All right, but how do we calculate it? Well, there are two ways. The first way, just like we saw with delta S, all right, we have a balanced reaction. We know the Gibbs free energy values for all those products. We know those Gibbs free energy values for all those reactants, and we can calculate it by adding up the products, using the coefficients, and subtracting out the reactants. All right, and if that case, your delta G value is negative, then you have a favorable process. That process is going to have extra energy at the end. It's going to get released out into the universe. The universe can use it to do something else, and the universe is happy. All right. That's one way to do it, but we don't always have all those numbers. So, another way is to look at how that free energy relates to the enthalpy and the entropy changes as part of that reaction or process. So, delta G equals delta H minus the temperature times delta S. I always tell my students, this is goldfish are horrible without tartar sauce. That's how I remember that formula, but it's also in your reference sheet, so you don't really have to memorize it. All right. Now, for this process, we want delta G to be negative so that that energy is released. The best way for that to happen is to have a negative enthalpy, which means that we've got an exothermic reaction and a positive entropy, because that minus T delta S, if delta S is positive, the whole thing remains negative. So we increase the negative value of delta G. That is a system that will always be favorable if you have an exothermic reaction that increases the entropy. All right. You can also have systems where it is not favorable. So delta G is going to be calculated to be positive. In that case, always happens if you have an endothermic process that decreases the entropy afterwards. In that case, always unfavorable. Now, if you're in between, so let's say you have a positive enthalpy and a positive delta S, then it's going to be temperature dependent on whether that process is going to be favorable or not. All right. If you have an exothermic process with a negative enthalpy value and you have a negative entropy change, so you decrease disorder, again, it's going to be temperature dependent as to whether you are going to get a favorable reaction or not. All right, so you need to pay attention to the signs of your entropy and enthalpy, and the temperature is very important in determining favorability for these processes. Remember, though, delta G wants to be negative, indicating that energy is released. All right, so this is our favorable set of signs, and this is our unfavorable. And in between, temperature dependence. All right, but the goal right here, negative delta G. Okay. All right, so we're going to work a couple different problems utilizing our understanding of delta G and entropy. All right, this first one at 25 degrees Celsius, yeast can produce ethanol by fermenting glucose, C6H12O6, as shown in the reaction below. Use the following information to calculate delta H, then delta S, and then delta G for the reaction run at 25 degrees Celsius. All right, now I cannot calculate delta G using my first formula up here. Whoops, using this formula right here. All right, I don't have those values, so I'm going to use that second formula to calculate delta G. But before I can do that, I need delta H and delta S. So that's going to be my first job. All right, so remember, enthalpy of a reaction is equal to the sum of the enthalpy values for your products times their coefficients plus the sum of your entropy, minus the sum of your enthalpy values for your reactants. All right, so first I'm going to look at my reaction. I have C6H12O6 aqueous, so that's going to be this value. C2H5OH liquid, so that's going to be this value, and then CO2 gas, and that's going to be this value. So I'm going to need these three values. So I start with the product side. So 2 times negative 393.5. All right, I'm going to leave my units out for right now because it gets kind of messy. And then I've got two CO2 molecules. Oh, whoops. I just switched by CO2 and H2O. Hold on. Let me do this the right way. All right, so back. Ethanol, 2 times negative 277.0 plus 2 times for my carbon dioxide, negative 393.5. All right, minus the reactants. I have a single glucose molecule at negative 1260.0. All right, so as I do the math there, I'm going to end up with negative 81.0, and my unit here will be kilojoules per mole. So this is going to be an exothermic process. All right, now I'm going to repeat, but this time I'm going to look at entropy. All right, so I'm still going to be using the same three components, but the entropy value this time. All right, same idea though. The change in entropy for the reaction in this case is going to be equal to 2 times 160.7 plus 2 times 213.7 minus 289.0. All right, so I'm going to add those up, and I have a positive 459 joules per mole Kelvin. All right, so we can see that entropy increased here. So we have an exothermic reaction and disorder is increasing. This is going to be a favorable process, which means I would anticipate my delta G value should be negative. All right, now before we move on to delta G, just a reminder to calculate that value, it's going to be the change in enthalpy of the reaction minus the temperature times the change in entropy. All right, so I want to take a moment to look at these units. All right, I have kilojoules for my enthalpy and joules for my entropy. You have to pay attention to this because that is how they are expressed in these tables, which means I need to convert one way or the other. It does not matter. Usually we like our energetics in kilojoules, so I tend to convert my joules to kilojoules. All right, so what does that mean for my calculation? I'm going to have negative 81.0 kilojoules per mole for my change in enthalpy minus T. Now, if you look at your unit for entropy, it's joules per mole Kelvin. So the temperature needs to be in Kelvin. 25 degrees Celsius is 298 Kelvin. And then 459 joules is 0.459 kilojoules, and that'll be per mole Kelvin. So my kelvins are going to cancel, and that'll leave me kilojoules per mole minus kilojoules per mole. All right, so I map this out, and I get a value here of negative 217.8 kilojoules per mole. All right, so we can see that our delta G value, whoops, is negative as predicted. So this is a favorable reaction. All right. If the reaction is run at a temperature of 5 degrees, is the reaction favorable in the forward or the reverse? All right. So I could do the math, right? I've calculated delta H, I've calculated delta S. I could do the math just like I did with delta G equals delta H minus T delta S. But, all right, because delta H is negative and delta S is positive, this reaction is favorable at all temperatures. All right. So because we have an exothermic process that increases disorder, it does not matter what the temperature is. It will always give you a negative delta G value. All right, let's move on to this next one. Here we have nitrogen dioxide gas decomposes to dinitrogen tetroxide gas in a reversible reaction. We've got our reaction right here. Oh, notice that it is not balanced. All right, I'm going to just go ahead and put a 2 there just in case. The enthalpy change is negative 58.03 kilojoules. The entropy change is negative 176.6 joules per Kelvin. What is the value of delta G? All right, so we are just going to use our delta G formula here because we have the enthalpy change, we know the temperature, and we have the entropy change, so we don't need to do any other calculations. All right, so negative 58.03 kilojoules minus, all right, we're at 298 Kelvin. All right, now again, you've got to watch these units. Right, we've got joules in there for entropy. All right, so I'm going to put in negative, but 0.1766 kilojoules per Kelvin. So that's going to fix my unit issue. All right, those kilojoules are going to cancel. All right, we're going to finish the math and we're going to get a value here of negative 5.40 kilojoules. Oops. All right, so this reaction is favorable, but it's barely favorable. All right, if we think about it, we have an exothermic process. The disorder, according to that delta S value, is decreasing. All right, so this is one of those setups where temperature is important. All right, if we change the temperature too much, we may make the reaction unfavorable by making that T delta S portion much more important than our enthalpy portion. All right. All right. At what temperature is delta G equal to 0? Okay, so I guess we're going to figure out what that temperature is. So in this case, we put delta G in as 0. We keep our delta H value at 58.03 kilojoules. And now our unknown is T. That's going to be what we're looking for. So we keep our negative 0.1766 kilojoules per Kelvin. All right, so we're going to move some things around. Then we're going to solve for T, and we find that 329 degrees Kelvin is when the delta G value is 0. All right, and as we move away from that value, we become favorable or unfavorable depending on the direction. All right, so would delta G be negative above or below that temperature? All right, so if the temperature is greater than 329 Kelvin, delta G becomes, whoops, positive, and the reaction becomes unfavorable. All right. So this reaction is driven by that temperature. All right. If we go above 329 degrees Kelvin, then that T delta S portion is going to be greater than the enthalpy portion, making delta G positive. And when that happens, the reaction becomes unfavorable. All right. So that means energy would need to be absorbed for it to occur. All right, for a particular process at 300 Kelvin, delta G is negative 77 kilojoules per mole, and delta H is negative 56.9 kilojoules per mole. Find the entropy change for this process. All right, so same general idea. We're going to use our delta G formula. So delta G equals the change in enthalpy minus the temperature times the change in entropy. All right, we have negative 77.0 kilojoules per mole for our free energy. And we have negative 56.9 kilojoules per mole for our entropy. I'm sorry, enthalpy. And we're working at 300 Kelvin. Unknown this time will be the entropy change. All right, so we're going to move the enthalpy over to the other side. Oh, I just see on my answer key I did it wrong. So we'll try it again. Okay, so we're going to move that where we have negative 77 minus negative 56.9. All right, so we're going to have negative 20.1 kilojoules per mole, and that's going to be equal to negative 300 K times delta S. All right, so we're going to divide by negative 300, and we get 0.067, and our units here are going to be kilojoules per mole Kelvin, and that's going to be our entropy change. Now, this is in kilojoules. Remember, we usually see these in joules. So if we convert it to joules, it's a positive 67 joules per mole Kelvin. All right. So what we see here is entropy is increasing for this process. We also have an exothermic process based on that enthalpy change. So free energy will be negative under all temperature conditions for this particular process. Okay, so you can see entropy is an important part of determining the favorability of our reactions. We had previously focused only on the heat energy, and if energy was going out, the universe liked those exothermic reactions. If energy was absorbed, those were less likely to occur. And the reason for that is this free energy idea, Gibbs free energy. It weighs the relative contributions of enthalpy and entropy, both of which are very important in determining whether a reaction is favorable as written. It's not just enough to know if the heat energy is going in or out. You also need to consider, is the process increasing or decreasing the disorder in its environment? All right. The formulas are pretty straightforward. The numbers are straightforward. Just watch those units. All right. Let me know if you have any questions.